Section 1. Work physics in action. Have you ever pushed a heavy box across the floor? It can be quite a challenge, right? If so, you have done work. But what exactly does that mean in the realm of physics? In physics, work has a specific meaning. It's not just about getting tired or sweating. Work is done when a force causes an object to move a certain distance. This is a fundamental concept in physics. Imagine pushing that box again. Think about the effort it takes. The heavier the box, the more force you need to make it move. This is because the force required is directly related to the weight of the object. The farther you push it, the more work you do. Distance plays a crucial role in determining the amount of work done. We can calculate work using a simple formula. Work, W, equals force, F, multiplied by distance, S, or W equals F times S. This formula helps us quantify the work done. The unit of work is the joule, J. This is the standard unit of measurement in the International System of Units. 1 joule is equal to the work done by a force of 1 Newton moving an object 1 meter. This gives us a clear understanding of how work is measured in physics. Section 2. Energy in motion. Kinetic energy. Anything that moves has energy. We call this kinetic energy. The faster an object moves, the more kinetic energy it has. Think about a speeding car. It has a lot of kinetic energy because it is moving fast. A bicycle moving slowly has less kinetic energy. The mass of an object also affects its kinetic energy. A heavy truck moving at the same speed as a car has more kinetic energy because it has more mass. Kinetic energy is the energy of motion. The faster and heavier an object is, the more kinetic energy it possesses. Section 3. Stored energy, potential energy. Sometimes, energy is not about motion, but about position or state. This stored energy is called potential energy. Imagine a book held high above the ground. It has potential energy because of its position. If you let go, gravity will pull the book down, converting its potential energy into kinetic energy. A stretched rubber band also has potential energy. This energy is stored in the stretched material. When released, the rubber band snaps back to its original shape, converting potential energy into kinetic energy. Potential energy is stored energy that an object possesses due to its position or state. Section 4. The power of energy. Power is the rate at which work is done. It is a measure of how quickly energy is used or transferred from one form to another. In other words, it measures how quickly energy is used or transferred. This concept is essential in understanding how different systems operate efficiently. Imagine lifting 2 identical boxes to the same height. This simple example can help us grasp the idea of power in a tangible way. You do the same amount of work in both cases. The work done is the same because the boxes are lifted to the same height. However, if you lift one box faster, you use more power. The speed at which you perform the work affects the power used. The unit of power is the watt. This unit helps us quantify and compare the power of different systems. 1 watt is equal to 1 joule of work done per second. This relationship is fundamental in physics and engineering. A more powerful machine can do the same amount of work in a shorter time. This efficiency is crucial in many industrial and technological applications. Power is a crucial concept in physics and engineering, as it helps us understand the efficiency of machines and processes. By understanding power, we can design better systems and improve existing ones. Section 5. Energy transformation from one form to another. In this section, we will explore how energy changes its form and the implications of these transformations in our daily lives. Energy cannot be created or destroyed, only transformed from one form to another. This is a fundamental concept in physics and is observed in many natural processes. This fundamental principle is known as the law of conservation of energy. Consider a roller coaster, a perfect example to illustrate this concept. At the top of the hill, it has maximum potential energy. This energy is stored due to its elevated position. As it races down, this potential energy is converted into kinetic energy, the energy of motion. The faster it goes, the more kinetic energy it has. As the roller coaster goes up the next hill, some of its kinetic energy converts back into potential energy. This continuous exchange keeps the ride thrilling. Throughout the ride, energy is constantly transforming between potential and kinetic forms. This interplay is what makes the roller coaster experience dynamic and exciting. Energy transformations occur everywhere around us. From the bustling city streets to the serene parks, energy is always in motion. In a car engine, chemical energy stored in fuel is converted into heat and kinetic energy. This transformation powers the vehicle, enabling it to move. In a light bulb, electrical energy is transformed into light and heat. This simple act of switching on a light is a daily example of energy transformation. Understanding energy transformations is crucial for developing new technologies and addressing global challenges such as climate change. By harnessing these transformations, we can create more efficient systems and sustainable solutions for the future.